Hello everyone, I would like to present about PostMesh graph convolutional network for 3D human pose and mesh recovery from a 2D human pose. The goal of PostMesh is to localize human joints and mesh vertices in 3D space from a single algebra image. In the literature, the data captured from the control setting has been valuable trained data because it has accurate 3D annotations such as 3D joint locations. However, the data has a domain gap problem because it has very different image appearance compared to in the wild images. On the contrary, 2D poses from the control setting and in the wild are relatively homogeneous. In this context, we decouple the task into 2D human pose estimation from an image and 3D human mesh estimation from a 2D human pose to solve the domain gap. PostMesh consists of PoseNet and MeshNet. PoseNet first lifts a 2D pose to a 3D pose, and MeshNet estimates 3D mesh coordinates from the poses in a coarse-defined manner using graph CNN. PoseNet is a simple network based on fully connected layers, which is based on ABS Pose Lifter and a simple yet effective baseline from 2017 ECCV. MeshNet is based on Chebyshev graph CNN and upsamples the concatenated human pose graph to our original human mesh graph in a coarse-defined manner during the forward propagation. To upsample the graph in a coarse-defined manner, we generate various resolutions of mesh graphs by coarsening a human mesh graph following Deferet et al. The coarsening process initially generates multiple coarse graphs from the original mesh graph and adds fake nodes without edges to each graph. Each level of a coarse graph has an exactly half number of vertices of the corresponding fine graph, and each vertex in the coarse graph has two children vertices in the fine graph. The numbers of vertices range from 96 to 12,288 and from 68 to 1,088 for body and hand meshes respectively. PoseNet and MeshNet are supervised by one loss function and four loss functions respectively. We train the PoseNet by minimizing L1 distance between the predicted 3D pose and ground truth root joint relative 3D pose. On the other hand, we trained MeshNet with a weighted sum of vertex coordinate loss, joint coordinate loss, surface normal loss, and surface edge loss. Vertex coordinate loss measures L1 distance between the predicted 3D mesh coordinates M and ground truth root joint relative 3D mesh coordinates. Joint coordinate loss supervises the network to estimate mesh vertices aligned with joint locations, and it measures L1 distance between the 3D pose regressed from the predicted 3D mesh M and the ground truth pose. The matrix J refers to a joint regression matrix defined in simple or MANO models. We used surface normal loss and edge loss to improve the surface smoothness and local details following pixel to mesh. We conducted extensive ablation studies to validate our method. We compared four different methods from the combinations of the regression target and the network design. As the table shows, our vertex coordinate regression scheme using graph CNN achieves the lowest errors while maintaining the smallest number of network parameters. Next, we compare the coarse-defined mesh graph upsampling scheme and the direct mesh graph upsampling scheme. As the table shows, the coarse-defined approach consumes half as much GPU memory during training and runs 1.5 times faster than the direct upsampling model in inference time. Last, we analyzed the cascaded architecture of PostMesh. First, A graph CNN that directly takes a 2D pose outperforms B, a cascading network that predicts mesh coordinates from a 3D pose output from pre-trained PoseNet without the concatenation. This implies a 3D pose output from PoseNet may lack geometry information in the input 2D pose. On the contrary, if we concatenate the 3D pose output with the input 2D pose as C, it provides the lowest errors. This explains that depth information in 3D poses could positively affect 3D mesh estimation. To further verify the superiority of the cascaded architecture, we explore the upper bounds of A and D, a graph CNN that takes a 3D pose. To this end, we fed the ground truth 2D pose and 3D pose to A and D as test inputs respectively. Apparently, since the input 3D pose contains additional depth information, the upper bound of D is considerably higher than that of A. We also fed state-of-the-art 3D pose outputs from Moon et al.'s method to D to validate the practical potential for performance improvement. Surprisingly, the performance is comparable to the upper bound of A. Thus, our PostMesh will substantially outperform a graph convolutional network that directly takes a 2D pose if we can improve the performance of PostNet. Here we compare our PostMesh with state-of-the-art methods. When we train all methods only on human 3.6M, image-based methods tend to suffer from the domain gap problem, while PostMesh provides the considerably lower error on 3D-PW, the in-the-wild body mesh benchmark. PostMesh still outperforms the state-of-the-art image-based methods by a large margin, even after we train all methods additionally on COCO, the in-the-wild 2D pose dataset. In addition, PostMesh achieves the lowest error on the 3D hand mesh benchmark compared to state-of-the-art hand mesh estimation methods. Finally, we give qualitative results of PostMesh. We experimentally verified that PostMesh can recover a certain amount of 3D body shape from a 2D human pose by training and testing PostMesh on surreal dataset, which has various 3D body shape samples. Here we provide PostMesh outputs on COCO validation set, which show in-the-wild body mesh results. These are qualitative results of hand mesh outputs on freehand test set. Last, we present the qualitative comparison between our PostMesh and the model-free part of GraphSML. We regard GraphSML as a suitable comparison target, since it is also the model-free method and the regresses coordinates of human mesh defined by simple using GraphCNN like ours. PostMesh provide more visually pleasant mesh outputs than GraphSML, as the figure shows. We summarize the presentation. PostMesh overcomes the domain gap between control setting and in-the-wild data using a 2D pose as input. PostMesh first lifts a 2D pose to a 3D pose and estimates 3D mesh coordinates from the pose in a coarse-fine manner using GraphCNN. PostMesh outperforms previous state-of-the-art methods in various benchmarks. PostMesh can recover a 3D shape to some degree. Thank you for listening.